Well, now we'll see how well we can do in terms of trying to do one of our labs. This one is your lab number 8, and it's an acid-base titration. And this has some of the review of the theory and all of that in this introductory part here. I'm sure you've downloaded all of it. And I'm sure you've also read through all of this initial part before about the definitions of strong acids, strong bases, weak acids, and weak bases, and how to do these type of calculations to get the different pH and pK and those different values. We also have the acid-base titration information on here, and the titration curves that you generate from all of that. But what I want to do is I want to get down to this portion right here in the pre-lab discussion. The other part you can do at your leisure. I just want to make certain that you understand this, and then I will give you some lab data to write down, and then you will have to carry out the operations with that information. First question is, a 20 milliliter solution of hydrochloric acid of unknown concentration is titrated with a 0.5 molar solution of sodium hydroxide. It requires 34.7 milliliters of the sodium hydroxide solution to reach the endpoint of titration. What is the concentration of the HCl solution? So the first thing is to recognize that in a strong acid, strong base reaction, that the hydrochloric acid and the sodium hydroxide is going to react 1-to-1 stoichiometrically. So that means if you have 0.5 molar solution of NaOH, that's 0.5 moles in 1 liter. And 1 liter is 1,000 milliliters. And what you have done is you've titrated that with 34.7 milliliters. So you'd multiply those three things together. It's 0.5 moles per liter times 1 liter divided by 1,000 milliliters times 34.7 milliliters is going to equal 0.017 moles of NaOH. So you've got 0.17 moles of that, and you added that to 20 milliliters of HCl. So that means that for that to be equivalent, it has to be 0.017 moles divided by 20 milliliters times 1,000 milliliters per liter to give you 0.85 moles molarity for HCl. That's 0.85 molarity, capital M. Okay? And that is the answer to there. What's the concentration? It's 0.85 molarity HCl. Now the next one is to determine the pH and the hydrogen ion concentration and the pH of a 0.2 molar HCl solution. So for that, because HCl is a strong acid, it completely dissociates. So a 0.2 molar solution will yield 0.2 molar H ion plus 0.2 molar chloride ion. And pH is simply the negative log of that hydrogen ion concentration. So the pH equals minus the log of and the concentration of 0.2, right? So the log of 0.2 gives you it ends up being a pH of 0.7, right? That's what that ends up being, pH of 0.7. Check that through in your calculator. So a minus log of 0.2 is 0.7. Now the next one involves a generic acid with a pKa of 6.3. Okay? So this is a weak acid. In what form would the acid exist as primarily at a pH of 8? in what form would the acid exist at primarily a pH of 5? So again, here you've got the HA aqueous going into the two separate ions. And the pH 8, the pH is higher than the pKa of the acid, so it exists primarily as the A- ion, right? Because all of the acid would have been neutralized by the base. At a pH of 5, pH is lower than pKa, so the acid would primarily exist as the HA, this side. So pH 8, it's primarily this ion. pH of 5, it's primarily this species. Okay? Just give you an idea of how those things are thought about. And what's the difference between the Arrhenius and the Bronsted-Lowry definitions of acids and bases? Well, the key there is that under the Arrhenius definition, acids produce hydrogen ions and bases produce hydroxide ions. Under the Bronsted-Lowry definition, acids are hydrogen ion donors and bases are hydrogen ion acceptors. So Arrhenius is in terms of H plus ions and OH ions, respectively, for acids and bases, whereas Bronsted-Lowry, it always depends upon the hydrogen ion being involved. So it is hydrogen ions as donors for acids and as acceptors for bases. Now, when we continue to move on to 5, the titration is used in the food industry, and I'll let you do that one for yourself. It's the same type of reaction or the calculations that you have to do in Part A. So you should be able to do that one by yourself. What I want to do is I want to get on to this procedure right here. It's not going to be exactly this, but read through the directions here about how we would have done this in the lab and what I would have given to you. And I would have given you these exact things. But instead, what I want you to do is go down to page 13 here, your data analysis. In this one right here, for the analyte on this particular one, the analyte is going to be 20 milliliters, that's 20.0 ml, of 0.500 molar HCl. You can stop, pause, rewind, and do whatever you need in order to write that down. But it's 20 milliliters of 0.500 molar HCl. The titrant that we're going to be using is 0.500 molar NaOH. So we're going to have a strong acid and a strong base. The concentration, the titrant is NaOH. Its concentration is 0.500 molar. So NaOH goes up here, 0.500 molar goes down here. What I'm going to do is I'm going to give you some burette readings, and you can calculate the volume of titrant added, and I'll tell you what the pH is for this particular one. You're starting off here at 45.00 milliliters. 45.00 milliliters. And this is a 0 here. The pH, we're fortunate here because we don't have pH meters. We would have just been using little swabs or things. Is 0.301. The pH is 0.301. In other words, that HCl is completely dissociated. Now, what we're going to do is we're going to add 5 milliliters here. So this is going to be 35.0 here. I'm sorry, we're going to be adding 10. So this is going to be 35 here, 10 less. So that means we added 10 milliliters here. Once we add 10 milliliters, this right here is only changed to 0.77 pH. Next, we're going down to and adding 5 more. So this is going to be 30 here, and this is going to be 15 milliliters total, because this is the total that we've added here. So this is 15. And so the pH is going to be 1.15. Then we're going to this one, and this is 25.0 milliliters. So that means we've added 20 milliliters here, exactly the number of milliliters that we had initially. So the pH here is going to be a pH of 7.00. We're going to add just a little bit more now. So this is going to be 24.8. Okay, so you can see how the values are dropping down here as we add more and more of the material. So the total volume added is now 20.2. This is going to raise the pH here to 11.3. The next one is going to be 20.0. So that means we've added a total of 25 milliliters. And the pH is now 12.91. And if we add 15, if this goes down to 15, or we've added a total of 30 milliliters, the pH is 13.5. Okay, I'll let you do the rest of this and plot out the information as you are supposed to do on this particular graph. Let's go on to this one right here for data analysis titration number 2. Here we're going to do a weak acid and a strong base. So here we're going to have, for the analyte, we're going to have 10.0 milliliters of 0.10 molar acetic acid, HC2H3O2. And for the titrant, we're going to have sodium hydroxide again, only here it's going to be 0.1 molar instead of the 0.5 we had before, so 0.1 here. Now I've got several more values here, because this type of a curve has a lot more changes in it as we go through these. We're starting off at 40 milliliters, and 45 milliliters here again, 45.00. And at 0 addition, our pH now is 3.00. For 44.00, in other words, we've added 1 milliliter, the pH is 4.05. If at 42.5, so we've added 2.5 total. This right here is 4.52. If we drop down now to 40 milliliters, 40.00, this means we've added 5 milliliters, and the pH is 5.00. So it's 5 milliliters, and this is 5.00. This is now 37.50. This is 7.5 added. The pH is 5.48. Continuing on, 36.25, 8.75 added, and this is now 5.85 for this one. Now we have 35.5, this is 9.5 added, and this is 6.28 pH. Then we go to 35.25. This is 9.75, and this is 6.59. You can see how we're slowly closing in on that pH of 7. And the next one gets us there. 35.10, 9.40 added, and this is a pH of 7.00. 35.00, in other words, 10 added, and this becomes 8.85. 34.90 is 10.10 added, and this pH is 10.70. And we'll have to continue on to the next part.